Welcome back to part 3, and can I just say thank you for getting this far. I admire your perseverance. This part 3 is not so long, bear with me, honestly it'd be worth it. Right, so we did the power checks. I forgot to mention that the power meter, oh it's gone. Okay, so this is just a quick view of what's going on inside. So this was before I potted it. Of course, Raspberry Pi there. Now this is a Raspberry Pi 4, so it's the full-blown Raspberry Pi, all powerful, all singing, all dancing. And this little baby is a Raspberry Pi Zero, so a little bit smaller, not quite as powerful, less connectors on it, but I managed to shoehorn it into the crank. So we've got Raspberry Zero, got a diddy little board here. That is the signal conditioning for the strain gauges. It's a high gain instrumentation amplifier and a 24-bit A to D. And then the battery goes here. Take that out. Little tiny DC to DC converter. So from 3 volts I'll get 5 volts, which drives the Raspberry Pi. So leave that out. And then I really wanted to avoid this, but there's the magnetic sensor for the cadence. Now it's the simplest way to measure cadence, just with a magnetic sensor and a magnet attached to the bike somewhere. So every time the magnet passes over this sensor, I get a pulse and I can measure the cadence. You can do some clever programming and work out what the cadence is based on power strokes, but that just takes a little bit more work. This was the easiest thing to do. So a few wires here to tidy up. And then we've got the strain gauges. So there's 2 there and 2 there. So it's a full bridge, a full Wheatstone bridge with 4 sensors. There's automatic temperature compensation. So because it's a balanced circuit, any changes in temperature, all the sensors, all the strain gauges respond exactly the same, so it compensates for itself. And that's basically it. I had to do a little bit of machining out to get the thing in, so this crank's not going to be used in anger, putting out massive amount of power on the road. It's just purely for evaluation and a prototype. So next stage after this is to fully encapsulate it so it actually looks like a crank. So we'll carry on from here. I did actually set it up to record data. So you know, like when you can press record on your Garmin head unit or whatever, you can do that on my power meter. So I recorded everything, and I can now show you a quick graph of the comparison between my power meter, and the Turbo Trainer power. There it is. So as you can see, not bad, not bad. You've got to remember, the price of this power meter, it was 30 quid. All the parts were 30 quid. The Turbo Trainer, 4-figure number. This part 3 now is the science. So let's get with the science. Like I say, it's not going to take long. And we'll start with a piece of wire. Right, piece of wire. Guy called Simeon Poisson, French guy, 18th century. He came up with this discovery that if you stretch this piece of wire, its electrical resistance goes down. It's actually quite tricky to squash a piece of wire, but he showed that you stretch a piece of wire, its resistance goes down. Bear with me. You'll see why in a minute why it's significant. Because what we're trying to do here, remember our crank. We're stressing this arm within its Young's modulus of elasticity. Right, okay. And what we find is weight, so we've got a force going down there, And we find that what we do is we just need to focus our attention on that. So what you're doing with a moment arm. So we've got a weight on there, right? It's fixed at that point. It's going to bend. It's going to bend there a little bit more than it's going to bend there or there. It's going to bend. You can't see it. Honestly, you can't see it, but you can detect it. What we get here, the atoms there, they're going to get stretched apart. Okay. So we have a tension force. Tension. The atoms there are going to get squashed. We have a compression force. Okay? Now, what Poisson came up with this piece of wire, you can think, can you link it now? All right, I'll help you. If we've got a torsion force there, remember the piece of wire, it's been stretched. And, all right, you can't do it, but a piece of wire here, a piece of wire in compression, it's been squashed. Right, like I said, I'll go back on what I said before. You can't compress a piece of wire, but imagine you can. So the resistance of this wire here, the resistance goes up, and the resistance of this wire goes down. So they're the key things to think about. Now, how do we measure that? This is where electronics come in. So, as the Americans say, electronics 101. Let's go for it. Potential divider. So, we have a resistor, another resistor, and we have a voltage source there. Right? Now, we measure the voltage there of V. That resistor there, R1, R2, okay? Let's assume that they're the same resistance, right? So the voltage there would be half V. No matter how much you pull on this piece of wire, you'll never be able to measure the change in resistance. It's so tiny. So we have to do some fancy things to try and increase the change in resistance. What we can do is, let me introduce the strain gauge. The strain gauge is what the power meter is based on. It's what all torsion systems are based on, all power meters, etc. It's basically, you've got two contacts there, and it's a long piece of wire. So it's copper wire on a flexible PCB, because this strain gauge is going to be bonded to the crank, and when it's bonded, and the crank bends a little bit, it affects the resistance of all these legs of the wire. So we get a good increase in resistance. So that's a strain gauge. So what we can now do, go back to the potential divider. We've got a strain gauge in there, fixed resistor there, ground. So strain gauge and fixed. So we can then say we've got V in. As the resistance changes on that strain gauge, so if the resistance drops there, the voltage there, so let's see, so R goes down, V out goes up. Right? That's from that equation that showed you before that you nodded off, fell asleep, you missed it. I'm not going to do it again. If the resistance goes up. So that's a resistance there. If the resistance goes up there, this V out will go down. Okay? It's a bit of maths. We won't get too hung up about it. Now, the biggest problem is, how do we measure it? V in, typically, let's say, 5 volts. Right. A strain gauge, typically 350 ohms. That's a unit of resistance. Greek. Okay. And we met that 350 ohms. That's fixed. Okay. So we'll get half of V out. So, oh, surprise, surprise, we'll get 2.5 volts coming out there. Okay. Now, when we change the resistance of that strain gauge, you won't even see it. I'm not joking. We're talking microvolts. For the full bending of a strain gauge, right, you might get 40 microvolts. That's 0.00004 volts. Right, teeny tiny. You can't measure that with a meter. There's no microprocessor that can measure that. So we've got a bit of a problem here. How do we measure that? So, because what we'll get is, it'll be 2.5 for no load, and then it'll be 2.5 full load. Right? Alright, so now you're thinking, the bright sparks will for amplifier. Yeah, well, let's amplify it. We'll stick that into an amplifier. What's an amplifier? Oh, another bit of electronics. Signal goes in, and we amplify it by, say, if we amplify it by, oh, just 10, right? So that 40 becomes 400 microvolts, still tiny. But what have we done? We've got 2.5 going in. We've now got 25 volts coming out. Now we're getting into, we're going out of the realms of digital electronics and computers and stuff. Computers, they don't work at 25 volts. So you can see, even with such a small amplification, we're amplifying this already fixed offset. Can't do it. But of course there's a way. And that was from Charles Wheatstone, English. He came up, well he didn't, he actually pinched the idea from some other guy, Christie, I think it was in the 18th century. Christie came up with this, what you call a balanced bridge, but it didn't get recognised. Charles Wheatstone, he then got it recognised. He must have had, I don't know, more powerful friends in wherever. The Wheatstone Bridge. Wheatstone Bridge. There's Wheatstone Bridge. Remember, we've still got, say, we've got R1 there. We've got R2 there. You've still got that potential divider there. So, say if we've got 5 volts going in, you've got 2.5 there. Now we've got R3 and R4. Another potential divider and 2.5 volts here. What is, if you've got your multimeter, your voltmeter, and you measure across this point and this point, what voltage would you get? 0 volts. Because you've got 2.5 there and 2.5 there. So you've got no potential difference. Now, this is where it's real. So simple, so simple. Now we can apply an amplifier, right? $128, I'll tell you why in a minute. Any change in any of these resistances here, any minute change, you'll get a small change there. Say if that one changes, you'll get a small change there, but that will stay at 2.5. So if that changes, remember what I said, you might get 40 microvolts. So if that goes to 2.5, no, 4, right? Because the 2.5 and the 2.5 have cancelled out, right? The 2.5 have cancelled out. We're only looking at 40 microvolts. That's what we're looking at for a full scale change. Full weight on there gives us 40 microvolts. Times that by 128, right? We've got about 5 millivolts there. Millivolts, like. Now there's a big change here. Microvolts to millivolts. 5 millivolts, we can actually start working with 5 millivolts. Okay, so that's the basic Wheatstone bridge op-amp configuration, right? And just a side note, we change that resistor there, but we can change any of these resistors. Now, if you remember that little diagram I showed you of the load cell, and I said there were 2 points there. If this point is in tension and this point is in compression, now trust me on this. So the tension, if we make that one tension, that one tension, so that stretches, the strain gauge there stretches, that resistance there reduces, that resistance reduces, and you get a double effect. That reduces, right, that stays the same, that reduces, so the voltage there goes up, that reduces, that stays the same, the voltage there goes down. So you get you've got a little bit of a double effect. Then if you do the same with this bottom one here, then in compression, you make that one compression, that one a compression, you've got a doubling effect. So you get the best of both worlds, and it's temperature compensated automatically, because any changes in temperature, because strain gauges, they're rubbish at temperature. It's a resistor, it's going to heat up. All these will heat up or cool down at the same rate, hopefully. So it's auto balancing. So there we go. We've got a full bridge, a full Wheatstone bridge circuit. So now we've got the op-amp. Sorry, not a precision instrumentation op-amp with a gain of 128. A to D. A to D, analog to digital converter. Digital number of the order of 2 to the 24 bits. We process that, we convert it into power. And that is it. The science is done. Well, thank you for watching. I honestly admire, if you have got this to this point, I admire your patience. But I've enjoyed doing it, I've enjoyed doing the power meter, and I really hope you've enjoyed the video. So give us a like, you don't have to subscribe, you can dislike it if you like. If you dislike it, tell me why, so I can improve it for next time. Oh my god. So, goodbye.